Hello everyone, welcome back. We are going to now talk about a problem for Riemann sum, lesson number 10 for BC Calculus, where delta x is not constant. So we're going to do an example now with that. It says the function f is continuous on the closed interval from 0 to 8 and has values given in the table below. It says use the trapezoidal approximation, so we've actually talked about that before. We cannot use the shortcut here because we'll talk about delta x in a second. And then I like this right here. This is the notation you guys are going to see in the next lesson when we start talking about fundamental theorem of calculus. So this is actually what the notation is going to look like to actually find the area underneath the curve. It tells us that we have three subintervals, and that just means we have three trapezoids that we're looking at: 0 to 3, 3 to 5, and then 5 to 8. And it tells us what it actually is. It tells us the approximation is equal to 20k. And we want to find the value of that k. So here's the first thing we got to do. We have to figure out what the interval from 0 to 3, what that value for trapezoid is going to look like. And so, ladies and gentlemen, remember that again, the area of a trapezoid is 1/2. And then remember that the height of our trapezoid is going to be delta x, right? And I've wrote this out several times in the other videos, so I'm just going to say it here. So the delta x between 0 and 3 is going to be 3. And then we talked about that, remember, that the base 1, this top base, is going to be the y value underneath the first one. So this is going to be 5. And then the second one, the second base, is going to be underneath the second. So k squared. So this is going to be, again, the 1/2. This is delta x, and this is going to be base 1 plus base 2. Well, base 1, again, would be when x equals 0, you go up to 5, that height 5. So that's why it's 5. And then if you go to x equals 3, our height is k squared. We don't know what that squared is. So that's what we get for that. So I'm going to go ahead and erase this piece, but that's what I did just to make sure you guys understand those numbers. So let's look at now the interval from 3 to 5, and we're going to repeat the same process. Well, we're going to go ahead and do the 1/2, because again, for a trapezoid, the equation is 1/2. Our delta x now in this case here is 2, and we're going to do the same thing. So we have k squared for 3, and we have 5 is 7. All right, so that's going to be it. So again, right underneath the 3 is the k squared, so that's going to be the height of our base 1, and then underneath the 5 is the 7. And then the last one we're going to do is from 5 to 8. And again, we have the 1/2. We have the delta x is going to be between 5 and 8, which is 3. And then we're going to go underneath 5. That base is going to be 7. And underneath the base of 8 is going to be 10. And so this one we actually can go ahead and add, right? Because we can do this. We have 7 plus 10 is 17. 17 divided by 3 divided by 2 is 51 over 2. Okay, 51 over 2. So now let's actually start setting this up. So let's do the problem itself. Okay, so let's go ahead and start setting this up. So the integration from 0 to 8 of f of x dx is going to be equal to, so we're going to go ahead and do these things. Notice, first of all, I'm going to go ahead and just pull up the 1/2. Okay, so I'm going to go ahead and pull up the 1/2 because they all have a 1/2. And so then I'm going to be left with 3 times 5 plus k squared. So that's going to be 15 plus 3k squared plus, because I'm just adding this one plus this one plus this one. So then I'm going to go ahead and do 2 times k squared. So this will be 2k squared plus 7. So it'll be plus 14. So I just distribute the 3 here. I distribute the 2. Remember, I've already pulled up the 1/2. Right? Pull up the 1/2. So I'm just going to go ahead and just this plus this plus this. And then we've already decided that this is 51. And so this equation is going to be equal to, it tells us what it's going to be equal to. It's going to be equal to 20k. And this becomes now an algebra problem. I'm going to go ahead and multiply by 2 just to get rid of the 1/2. So this right side here is going to be 40k. And then I'm going to start simplifying in the middle here, and I'm going to be left with 5k squared plus 80. And so, ladies and gentlemen, now we come to an algebra 1 problem, right? We just have to factor. So we have 5k squared minus 40k plus 80 is equal to 0. We can factor out of 5. We get k squared minus 8k plus 16 is equal to 0. And 5 doesn't matter, so we're going to factor k squared minus 8k plus 16, and we get k minus 4 squared. And so k has to be equal to positive 4. And so this answer is going to be A. So if delta x is not constant, so delta x in this case is not constant, then you have to write them out individually. You have to write them out individually. And then, you can still always pull up the 1/2, but you got to be very careful. You can't, you got to just make sure that you guys do individual trapezoids and then go ahead and either simplify doing that, or they give you a value that we can set it equal to. All right, so that's our first example for that problem. So hopefully that makes sense. So I just want to go ahead and just talk about question number 8 and question number 9 in your note packets. It's just a lot to write down, so I just went ahead and just show the answer key to what it is and just talk about it for a second. So for question 8, it says the object has a 0 initial velocity. So again, that's why we can put a 0 here for this. And it has a constant acceleration of 32 feet per second squared. And these are the units that you guys know from particle motion. And so we are able to then at 1, right, at time equals 1, we have 32, right? 32 feet per second. And so we're taking the number here and we're going to multiply it by the number you see here. So 1/2 of 32 is 16. 2 times 32 is 64. 3 times 32 is 96. And then 3.5 times 32 is 112. So you guys get the idea with this. Since the delta x is constant, right, and it tells us the distance traveled for seconds. So we were not told which ones we're going to use, so I went ahead and just showed you guys the left, the right, and the trapezoidal. And since delta x was constant, we can use our shortcut. So this, again, I'm going to use that 1/2 is the delta x. So I'm going to clarify that this is the delta x. And then remember, for left, it's all the numbers on the left except for the very last one. So it's every number except for the one that's on the right, the very end on the right. So we're going to add 0 plus 16 plus 32 plus 48, etc., up to 112. The right Riemann sum is the exact same thing, except for we don't use the first term, we use the last one. So we use all the numbers on the right except for the very first one. So we start at 16 all the way to 128, and we get the numbers right here. And the trapezoidal, remember again, 1/2 because of the trapezoid. This 1/2 is because it's delta x. And then we add the first one and the last one, and we double everything in between, and we get the answer as 256. And remember that this is the average of these two numbers that you see right here. About midpoint for a second. So I purposely left that one off because this one. So for midpoint, we want to actually look at, I can't do 8 rectangles. I can't do 8 rectangles because I don't know what's between 0 and 1/2. I don't know what 0.25 is. So for midpoints, what they're going to usually tell you is just say, okay, you want to do 8 for this one, 8 for this one, and 8 for this one. And we're going to tell you this. We're going to tell you how many rectangles we want. So we're going to just do 4. We want 4 here. So that means that our delta x is actually going to change. Instead of going for 1/2, if we want 4, our first one is going to be right here from 0 to 1. Our second one's going to be 1 from 1 to 2. Third one's from 2 to 3. And the third one's going to be 3. It's going to be 3 to 4. So what's going to be the value we're going to use is what's midway between that, which is going to be this value right here. So delta x is going to be 1. It's going to be double this. So be careful with that. And then, ladies and gentlemen, very easily, how do I find my values? It's always going to be every other one. It's always going to be that. Midpoint's always going to be that way. So when I ask you guys to use the midpoint Riemann sum, then you're going to use those numbers right there. It's always going to be every other one. So whenever you guys have a chart, it's going to always be the one that's the even one. So it's going to be 2, 4, 6, 8. They're never going to have it where it ends like this. It's going to always be every other one, and you will always have one to the left and always one to the right. So that's how you're going to find the midpoint. And then lastly, ladies and gentlemen, example number 9, it says from 0 to 1, a bug is crawling at a velocity determined by the formula. So it gives us the velocity formula where t is in hours and v is in meters per hour. It says find the distance that the bug travels during that 10-minute increment. And so since we're looking at it every 10 minutes, and again, this goes back to our units, we're looking at our function is actually in terms of hours, and we're looking at 10 minutes. So we have to convert our time instead of doing 10, 20, 30, 40, 50, 60. We want to go 1/6 of an hour to 1/3 of an hour, which is 2 over 60. This is 30 over 60, et cetera, et cetera. So this is the time frame that we want to use. And then we plug these values into our function to get the actual velocity. And so that's just really quickly, I don't want to waste time doing that, but that's how you do these problems, is that, again, make sure your units match, and then once you have your t values, you plug them in, and usually the charts are going to be given to you, because this just takes too much time, but at least this is how you solve the values if you don't have the chart. And then we've talked about this before, delta x is constant, so with the left, the right, and the trapezoidal. And for trapezoidal, I didn't even find that one because I just knew it was going to be the average of the two. So actually, let's look at midpoint for this one, just like we did in example number 8, midpoint for this one. And so our delta x would actually be, instead of 1/6, it would be 1/3, right? It would be the first and the third, the difference between this. So delta x would be 1/3. And then I would use the ones in the middle, to find my values. So midpoint would be 1/3. And then I would just take 6/7. I would add to that 2/3. Again, I would use a calculator for this, and then add 6/11. And just like in the previous example, ladies and gentlemen, it's every other one. It's going to always work out beautifully like this for us. So that's what we do. So that's enough is for Riemann sum, and we're going to come back in the next lesson and start talking about the fundamental theorem of calculus. So I will see you guys in the next video. Take care.